In this lecture, we are going to see very interesting part, power factor and capacitor bank mystery. Yes, it is a mystery. Most of the engineers or technicians are not aware about this. And though they are aware, they are not aware why. So we are going to see why. Why capacitor banks must be shut down during generator operation. Mystery, right? Okay. Now, see what happened exactly. We will see one incident. The $2.3 million mistake. This happened. What happened? In a tier 3 data center facility. Data center is a critical facility, right? Data center. Then engineers left capacitor bank online during emergency generator operation. See, during normal scenario, when your electricity board or city power is on, supply is feeding, then capacitor banks should be operating so that it will correct the power factor. So these EB board will not charge us penalty. So capacitor bank is very much important. We need to maintain the power factor. But when DG kicks in, then you should switch it off. Then what happened? Within just 30 seconds, voltage spiked to 150 of nominal voltage and destroying. What destroyed? See, critical UPS system at high voltage, such a 150%, it will not survive. Okay. Then server power supplies in the servers gone. Distribution equipment. Then 85% of engineers don't understand why this happens. And we are going to see why. One simple action would have prevented 2.3 million disaster to switching of the capacitor bank. Now, we will see in part 1 what we will master: alternator physics. Why alternators generate reactive power fundamentally differentially than utility grid. See, utility grid also there are generators, alternators. And why this alternator? Here also alternator we have on diesel generator. So what is the difference exactly? That we will see. Then voltage regulation, how capacitor banks create voltage regulation nightmares during generator operation. It regulates the voltage, that we will see why. How? Then leading power factor. The dangers of leading power factor conditions can destroy expensive equipment. So what is this leading power factor and how it is destroying the equipment? That we are going to see. And last is protection strategies. How to protect our equipment from this automatic control solution that prevent millions of dollars mistake. Okay. Now we will see utility grid versus generator operation. The critical difference, utility grid operation, what happens? Infinite bus is infinite, okay, with effectively unlimited capacity. Its capacity is unlimited, there is no limited capacity. Maintains constant voltage regardless of reactive power flow. It has all automatic mechanism to maintain the voltage. Okay, so it will maintain the constant voltage. It will not allow voltage to dip down. It will maintain itself. Can absorb or supply reactive power as needed. So it also has capacitors. If you have seen the 400 kV or 500 kV big substations, there you see on the transmission lines, towers, the capacitors are hanging. So every transmission line has capacitors. So these capacitors can absorb or supply reactive power. So they have done this arrangement already. Now, capacitors banks are heroes, improving power factor, reducing demand charges. In this case, it will reduce the power factor. It will not give the load on those transmission capacitors. So it will manage. So those are heroes. We are what doing? Improving power factor in case of utility grid operation. Now, what happens during generator operation? Limited reactive power capacity. Reactive power capacity is limited. Voltage controlled by automatic voltage regulator, AVR. We have seen in AVR module, voltage regulation. Voltage is regulated through AVR automatically. Then terminal voltage varies with reactive power load. If reactive power increases, then what happens? The voltage will go down. If it decreases, voltage will go up. So these are the problems. So capacitor banks become villains, creating instability and equipment damage. It becomes a villain because reactive power feeding. We will see in detail in next slide how reactive power flows and changes everything. Change everything. Normal utility operation, capacitors provide reactive power to the grid. Reactive power is provided to the grid. In generator operation, capacitor injects reactive power back to alternator. Here grid is there. Okay, all capacitors to absorb the reactive power. Capacitors are there. But in case of generator line doesn't have capacitors to absorb your reactive power, right? Okay. And then here what happens? Power flows from capacitors to inductive load. From capacitors to inductive load, power flows. If you have inductive loads, see, you have inductive loads, you have capacitors. What happens this cycle? Every half cycle, the inductive load is fed by capacitors, and next half cycle, again inductor will discharge to capacitor. Okay, just understand in detail this fundamental. See, in one cycle, capacitor will provide power to inductive load, then this coil is charged. Inductive load means what? Coil. Then in next half cycle, this will discharge, the magnetism will discharge and capacitor will absorb. So this cycle is happening. So reactive power is compensated inside the circuit, inside our premises. It is not going fed back to the utility. So in utility also they have inductive loads, they have capacitors, both the things. If you have more inductive load, then capacitors will communicate or feed the power through grid because they have transmission capacitors, I told you. Again they have inductors as well, but this will be at cost. Okay, the capacitors as well as if inductors are there, then what will happen? Those capacitors will get discharged. If you are in this thing, any which ways, you check your inductive load and then put the capacitors right at the same capacity of the same capacity. You will see calculation I have given. One HTML sheet is given along with the modules. Just check that how to calculate the capacitor bank capacity. Okay, it is interactive, very interesting. So in that we come to know how much capacity capacitor bank we should install. Now first, you have now installed during the utility operation, you have capacitors. Now capacitors, let's say your inductive load is not up or momentarily it is not up. Then what will happen? It will feed to the grid. Grid also has inductors. So it will absorb your capacitor reactive power, and then next half cycle it will again supply to capacitor. And then if your inductor kicks in after some or next moment, then the cycle will be shortened. It will be inside your premises. So this is the power juggling between capacitive and inductive. You need to understand it in detail. Try to search on inductive and capacitive reactive powers, how they do the juggling of energy. Okay. Now, what happens? Grid voltage remains stable regardless of flow, because inductors are there, capacitors are there. So it is maintaining the voltage. Here, AVR detects rising voltage, reduce excitation. What it will do? It will reduce the excitation. Then what happens? Your voltage level will go down because of capacitor, voltage will go up, and it will sense voltage is up. Why should I increase the excitation? And excitation, we know in that video also at the start of this model, As excitation increases, your voltage increases. As excitation decreases, your voltage decreases. So AVR detects rise in voltage and it will decrease the excitation. Now ultimately your entire voltage will go down. Now then, reduced excitation creates instability. So if voltage is not proper, what will happen? Power is constant. Let's say P is equal to voltage multiplied by current, V into I. Then current will go up. Your equipments will not work. It will heat up. Heat losses, I square R losses, because I is going up, R is constant. So these are the problems because of capacitor. Then the result, what is the result? AVR and capacitor bank fight each other. AVR and capacitor bank will fight. It will increase the voltage, it will decrease. Okay. Again, it will increase the voltage. So it is fighting each other. Voltage oscillates 440 to 520. Increase, decrease, increase, decrease. Then control system instability. Control system will get confused. What is happening? Voltage levels are like going up and down. Then equipment damage within seconds. That's what we have seen. What happened here? Equipment damaged in 30 seconds because of this oscillating voltage. Energy transfer, energy taking, giving back, taking, giving back.